It's what, an ordered list of numbers, right? It's a list. It's a list. And so then if that list hones in on a particular value as you go way out in the list, right? If you get closer and closer to a number, we say that sequence converges to a limit, right? Converges to a limit. All right, and so you did lots of homework on that. So then what about a series? What is a series, first of all? What is a series? What is a series? So these 3 weeks of the class or 4 weeks of the class mean nothing if you can't say immediately what a sequence is and what a series is. All these details and algebra and rules and memorization, it's all for naught if you can't just tell me, boom, a sequence is this and a series is this. What is a series? Yeah. Right, so if you have a sequence and you just add them all up, you just add up all those things, that's a series, right? That's a series. So what does it mean for a series to converge? A series to converge means when you add up all the terms in the list of the sequence, what, you get a finite value. You get a finite value. Is that possible? If you have an infinite sequence to add up an infinite number of things and get a finite value, is it possible? Well, it better be if we're going to talk about that, right? See, it seems a little counterintuitive, right? You're going to add up an infinite number of values, and and that sum will be a finite value. Oh, really? Right, you keep adding and adding and adding, so how is this possible? So we're going to see. All right, so let's represent, I'm going to give you I want you to represent this, represent the sequence, the series, and the sequence of partial sums for this sequence. So, but only in such a way that a third grader would understand it, right? So what's the sequence, what's the series, and what's the sequence of partial sums? And what you're writing is what a third grader would understand if they understood fractions. Okay? So okay, so the sequence. Jamie, did you get the sequence? Okay. Yeah, the final value is great. No, but I love that you told me how you did it. That was great. But okay. And on and on and on. Agree? 12/5, okay? It's the list, right? It's the list. I equals 1, I equals 2, I equals 3, I equals 4. Each of those I values gives you a term of the list, and then we make the list, okay? And then, what is the series? What is the series? Yeah. Right. You're going to do 3 halves plus 12/5 plus 27/10. This is all review, right? Sequence of partial sums. Sequence of partial sums. Yeah?
3 halves, comma, 3 halves plus 12/5, comma, 3 halves plus 12/5 plus 27/10, comma, dot, dot.
Right. So the partial sums are first term, sum of the first 2, sum of the first 3, sum of the first 4, right? So you make a list, you make a new list by adding the first however many I terms. Okay, so this sequence, does it converge or not? You guys are experts at sequences now. Convergent, does it converge or not? Yes, and what does it converge to? 3. So I'm going to take this and I'm going to say, suppose we went out to the millionth term. What would that number be like? He said pretty dang close to 3, right? So I'm going to show that this way. Is it technically 3? No, but it's super close. And what about the next one? Even closer. And then even closer. Every term is a little bit closer to 3. So I'm going to write that this way, that when we get out to the millionth, the billionth, the trillionth term, we essentially have a list of 3s, right? Technically, we know they're not 3s, but they're so close that I'll write it this way. So then what about this series? It's thinking about that sequence. I'm going to add up all infinitely many terms. So what do we say? The series converges if you get a finite value when you add them all up together. What do we think? We're going to get a finite value when we add all these up? Why? Because in the end, what's happening? We just keep doing what? Adding 3, essentially, right? We keep essentially adding 3 over and over and over again. So immediately you should think, oh no, this could never, the sequence converges to 3. Those values are getting closer and closer to 3. But then if you add all those up, in the end, it's like you're just going 3 plus 3 plus 3 plus 3 plus 3, and that's just going to keep getting bigger and bigger. Okay? So then what about the sequence of partial sums? What does that have to do with it? So how does that relate to the series? So I'm going to make this sequence where each term of the sequence adds on another term. Each time I'm adding another term of the sum. So how can we talk about what's the relationship of the sequence of partial sums to the series? Kenny has an idea. Anybody else? What's the relationship of this sequence? Think about this sequence. We keep adding another term and another term and another term in that sequence. What's its relationship to the series? Daniel, any idea?
It's a summation. Each term is a summation of up to that k.
Right, so like say we go out to the millionth term of this sequence. How will that relate to the series? The first million terms, right? And then the billion, the first billion terms. And then the trillionth, the first trillion terms. So what is that relationship between that? Maybe the next example will make that more clear. What's that? It's like the accumulation for the series? Yeah, so it's like an accumulation kind of function, right, for that series. Okay. All right, we'll put that question on hold. That might be the answer might be clearer when we do the next one. Okay, but so clearly this series does not converge. It just keeps getting bigger and bigger indefinitely. Essentially, you just keep adding 3. So that can't converge to a finite value. Those are the questions we asked. Okay? New one. How about this? 4 over I squared plus 2. 4 over I squared plus 2. So quickly, the sequence is 4/3, then 4/6. One more. 18ths? 18ths? Okay. The series would be just add those all up, and we know what the sequence of partial sums would be. Let's write out the sequence of partial sums. So we know the series is the sum. So the sequence of partial sums is 4/3, then 4/3 plus 4/6, then 4/3 plus. Okay, does the sequence converge? Does the sequence, the original sequence, does it converge? 4 over I squared plus 2. He's saying it converges to 0. Do you agree? And how do you know that?
Because the denominator gets
Okay. And what kind of sequence is this really close to? It's really close to what kind of sequence? P sequence with? So it's like a P sequence. It's not a P sequence because you go +2, but the +2 is pretty kind of inconsequential. So it's very, very much like a P sequence with P equals 2. Therefore, converges to 0 because P is greater than 0, right? As long as P is positive, that exponent is positive, that will converge to 0. Okay? So these values, when we get out to the millionth, billionth, trillionth term, what? They're a whole lot like zeros when you go way, way out in the sequence. Are they zeros? Technically, no. But they're so close, and they're always getting closer to 0, right? They're super, super close to 0, always getting closer. All right? What about this? Does the series converge now? What's that? Yeah.
Yes, because after a certain point, you're essentially just having 0.
Right. Okay, so this is the idea of how a series can converge, is if you keep adding essentially 0 or a super, super small number, then it won't roll off to infinity, right? So the sum won't just keep getting bigger and bigger. Okay, so now let's talk about the sequence of partial sums. We keep adding one more each time when we make this list. So if we go way, way out there, say to the millionth term of the sequence of partial sums, or the billionth term, what can we say about this sequence relative to the series? What's the relationship between this sequence and the series? What's that? The closer to, but we're talking. So if we think about what the sequence of partial sums is, you should be thinking kind of like, well, as you chase that sequence out, it's kind of like is the series. Right? Because what do you do? With each term, you just keep adding one more. You keep adding one more. So it's like, if you could take it way, way out, it's kind of like you're doing the series, but in sequence form. Do you see that? So therefore, the limit of this sequence is what? What's the limit of the sequence? If you just keep adding on terms and take that forever, the limit of that sequence would be what? The same as the sum of the series. Do you see that? What the sum is. So if you understand the sequence of partial sums and you think about it as a really, really long list, then you should think, oh, that basically is the series, just in a list form instead of just one big lump sum. It's a list that keeps getting what? Closer and closer and closer to the value of the whole sum by adding one more each time. Yeah.
Wait, could you repeat that statement? You said the limit of the series is equal to what again?
The limit of the sequence of partial sums. What is it? You tell me what it's equal to. You just keep adding on another term of the series. You just keep going and going and going. So what's the limit of that?
Right.
What's the limit? Where does that head to?
I'm not sure.
It heads to adding all of them up. And what's that? The series. The series, right? Right? If we make a list where you keep adding one more each time, and then you take that to the end, well, you've added them all up.
Oh, so
And that's the series.
the limit of the series is equal to the limit of the partial
Sequence of partial sums.
Sequence of partial sums, not the sequence. Right?
Not the sequence. No, the sequence is the list of the original values.
That's what I.
Okay, so here we go. So the infinite series converges if the sum of the series is a finite value. And here's this important point. The sum of the infinite series is the limit of the sequence of partial sums. And if you understand the sequence of partial sums, if you really understand it, that should be a no-brainer. It's like, oh, of course, that makes perfect sense. So if that's still hazy, then go back and review and practice on sequences of partial sums and think about what that is. So let me show you this in graph form. This can help. I'll show you a graph that kind of illustrates this point for these two sequences, C and D. All right, so here's that original C sequence and the D sequence. I just use J instead of I, okay? And so what I want to graph here is on the x-axis, I'm going to graph the value of I. And on the y-axis, for each value of I, I'm going to graph the partial sum, the ith partial sum. Okay? So there's the ith partial sums. There's a blue and a red dot. And remember what? This one sequence approached 3, and this sequence approached 0, right? So with every partial sum, again, the y values of these points are the partial sums, right? Adding up the first I number of terms. So the blue graph, which is the blue graph, C or D? You should be thinking C, because what happens? Every time we advance to the next I, we add essentially what? A number getting closer and closer to 3. So the amount that it goes up each time is essentially this 3. But what about the red graph? So what's happening here? So the amount that we're increasing by is getting closer and closer to 0. That sequence is approaching 0, so that the amount that we increase by every term in the sequence of partial sums gets smaller and smaller and smaller. And so then what happens? When you keep adding a smaller and smaller number that approaches 0, then that sum will level off, right? That sum will level off. All right, I'm only showing 10. So then I made a table of the sequence of partial sums for the D sequence, the red one. Small, but I'll zoom in on it. Okay, so here are the partial sums. 4/3, 2, 2.36. When you get out to 10, the partial sum is about 3.06. When you get to 50, it's about 3.36. So I just kept making I bigger and bigger. So the sum of the first 300 terms is 3.43. The sum of the first 350 terms, 3.43, a little bit more though. And then the sum of the first 3,000 terms, 3.44278. Okay? And look at the difference between the 400th and the 3,000th term. It's like less than 100th, right? So this is the idea that the sequence is approaching 0. What we add each time is getting super, super small. So by the time you get to the 3,000th place, we're kind of really honing in on a particular sum, right? We're really honing in on a particular sum of terms there. That's the answer? What do you think? That's the answer? So is this the sum of the series, 3.44278?
Oh, no.
But what about it? It's really, 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 really close. Okay? So yeah, we could take it to the 30,000th term and the 3 billionth term, and all we would be doing is fine-tuning more and more decimal places, right? All you would be doing is getting it closer and closer by fine-tuning more smaller and smaller fractions of this number. But yeah, to the nearest hundredth, this is correct to the nearest hundredth. So notice this. So the sequence of partial sums, yes, its limit is the series, but each one of those partial sums is like an approximation. And the further out you go, the higher the longer the partial sums with more terms. The more terms in your partial sum, the closer it is as an approximation to the series. So this is a really, really good approximation of the series, the 3,000th partial sum. So if I'll turn that on, 3.443 as a really good approximation, and you see that that's where it's leveling off, right? And so if we were at the 3,000th term, the red dot at the 3,000th term would look essentially on that line. Yeah.
So is it kind of like sequences in that, like, it approaches some term and we know it's like an approximation, but like it's not the actual number?
Well, any particular partial sum is approximation. But the limit of the sequence of partial sums is the same as the series. The limit. Like if you were to add all infinitely many terms together, or take the infinite term of that sequence, it would be the same as adding them all together.
Okay.
That's what we mean by limit, right? The limit is like where it's going, what you're getting infinitely close to.
So if we were to add all the infinite numbers, then it would be exactly 3.43 something, or 4.43.
4 something something something, right? Yeah. The further you go out, the more decimal places you get correct. If you could add all infinitely many terms, you'd have every decimal place right. It'd be exact. Okay, does this make sense? So this brings us to a really important conclusion. The divergence theorem. So looking at those two examples, the divergence theorem lets us conclude quickly that an infinite series diverges if that sequence has a qualifying feature. And those last two examples pointed that out. So you're looking at a sequence, and you're asking if the series converges or not. What could you see about it that you'd say, no, that diverges? That series would diverge, given this fact about the sequence. What fact about the sequence could you say, boom, that series could never converge? Okay, that's true.
Well, if the sequence converges to a number that's not zero.
She said if the sequence converges to a number that's not zero, or diverges, yeah. Right, so if the sequence converges to something that's not zero, then what happens? You just keep adding that number over and over again. That sum could never converge, right? Or if the sequence diverges, yeah. So the kinds of sequences we could immediately conclude that the associated series diverges is sequences that converge to something other than zero and sequences that diverge. And this is the divergence theorem. The series diverges if the sequence does not converge to zero. And that's what those last two examples just illustrated. So this should be the first thing that we check, right? This is the first thing we're going to look at in the sequence. Because if that sequence doesn't converge to zero, we're done, right? Game over. Series cannot converge if the sequence does not converge to zero. Again, this should make sense. This should make sense understanding sequences and series. Any questions on that? So this will be always the first thing we check. We'll always use the divergence theorem. Before we go any further about analyzing a series, that sequence needs to converge to 0, or else there's no way the series could converge. All right, so let's talk about something called the harmonic series. Harmonic series is real basic series. It's just 1 over j. Or you could say 1 over j to the 1. If it's 1 over j to the 1, what kind of sequence is that, 1 over j to the 1? What kind of sequence are we adding up there? What's that? Is it a p sequence? You said a p sequence. Yeah, that's a p sequence with p equal to 1. So that's what the harmonic series is. It's a p sequence with p equal to 1. So you see that, you think what, right? See that, think what? Write out what it means. Write out what that means. You see all those scary symbols? They're not scary to you because you know exactly what it means. Write it out. Emily, can you tell me? Okay, so okay, so then mathematically, could you tell me what that's equivalent to? You see those symbols mathematically, what does it equal? But what, like I'm saying, equals what? Like, what are we going to write out that that's equal to? Brian, you tell me? That. What that? I want you to tell me what that means. Right. This. 1 over 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, right? See that? Think that. And that should be immediate. You see that? That's what's in your brain. That. Okay, what about this sequence? Does the sequence go to 0? P equals 1. Sequence goes to 0? Okay, so what about the series? Does it converge or diverge? Converges. Okay, I'm going to show you, so we know it's P sequence. Yes. Okay, those are the questions I just asked. Go through that. Okay, so I want to compare it to this sequence here. So what I've done is, so here's 1 over 1. Those are the same. 1/2 is the same. But instead of doing 1/3 plus 1/4, I want to do 1/4 plus 1/4. What is 1/4 plus 1/4? 1/2, right? How does 1/3 plus 1/4 compare to 1/4 plus 1/4? Is 1/3 plus 1/4 bigger or smaller than this? Bigger. Just think pizza. You'd rather have this amount of pizza than this, right? This is more than 1/2. Okay, then I'm going to take the next 4 terms. Instead of doing 1/5 plus 1/6 plus 1/7 plus 1/8, I'm going to add 4 1/8. And what's that equal to? 1/2. And how about what we have in our harmonic series? Bigger or smaller than 1/2? Bigger than 1/2. Then I'm going to take the next 8 terms. Instead of 1/9 through 1/16, I want to add 8 1/16 equals 1/2. And then our 8 terms compared to that? So this is 1, this is 1/2. The next 2 terms are greater than 1/2. The next 4 terms are greater than 1/2. The next 8 terms, greater than 1/2. The next 16 terms would be bigger than 1/2. Will I ever run out of terms? I can always take twice as many and add them together and conclude that that next chunk of terms is greater than 1/2. Conclusion? What's that? The series diverges. Does it diverge? Yep, because I'm never going to run out of terms. I can always take twice as many as I took before and conclude that that little sum is greater than 1/2. And then I can take twice as many as before. And I can conclude that sum is greater than a half. So when I add all of it up, is that going to converge? Nope. That's going to be an infinite sum. Uh-oh. What happened? I thought if the sequence went to 0, our series was supposed to converge. So that wasn't true. That's not right. Because I'm showing you a sequence. The harmonic sequence, 1 over j, definitely converges to 0. But when you add them all up, it's infinite. It's still infinite. So we need to revise our hypothesis about this, or revise our understanding. If the sequence doesn't go to 0, then what's true about the series? If the sequence doesn't go to 0, then the series diverges. What about if the sequence does go to 0? Now what's our conclusion? Maybe. Now it's like there's a chance, right? It might or it might not, because I showed you an example where the sequence went to 0 and it converged. But here's an example where the sequence goes to 0 and it doesn't converge. All right, so now so when your sequence goes to 0, it's like, okay, now we have some work to do. We got to figure out, does the series converge or not? It's just not as simple as, oh, the sequence goes to 0, therefore the series converges. No, it's kind of like it's maybe. Some do and some don't. Does that make sense? Yeah.
Where did the bottom series come from?
I just made it up in order to compare it to this. So this one is just like 1/2 plus a half plus a half plus a half. But then these are all greater than, those same chunks are greater than a half. They both diverge, right? They both diverge. But this one is even bigger than this one. So it just, it's kind of a clever way to show that that diverges. Okay, so here's the big conclusion now. So now we've revised our understanding of this. If the sequence converges to 0, then what? The series, adding them all up, might converge. You're telling me there's a chance. Please.
And this is probably related to the title problem. So
Yeah, we're gonna get that at the end. We're gonna do that. Yeah, we're gonna go do that at the end. If I can get through everything. Okay, so P series are series from P sequences. So we just saw what? When P equals 1, what happened when P equals 1? Did the series converge or diverge? Diverge, right? We just showed that. So recall the P sequence, as long as P is positive, the sequence converges, right? That's the sequence now. And that converges to 0, right? So what about P series? We just saw the P series, the harmonic series diverges. That's the P series with P equals 1. So for what values of P does the P series converge, right? So we know with 1, it diverges. So what about something like 1/2? What if P was 1/2? Why? Why was it diverge?
That's the same thing as
same pattern, but at a slower pace.
So let's compare this to, we know the harmonic series diverges. So how does this compare to the harmonic series? How each of these terms compare how to the terms of the harmonic series? How does 1 over square root of 2 compare to 1/2 and 1 over square root of 3 to 1/3? Are these all bigger or smaller than these?
Smaller, but they're still pretty
Tom's bigger because Tom made it smaller.
Yeah, these denominators are smaller, which makes each of these terms
big.
bigger. So we know that the harmonic series diverges, and now we have a series, all of whose terms are bigger. Therefore,
Therefore, P has to be greater than 1.
okay, so yeah, so certainly we know P equals 1. So if P is less than 1, it's going to be even bigger than the harmonic series. So it's going to diverge, right? So whenever P is less than 1, like this example, 1/2, you're going to have a bigger sum. So this is the idea of comparison. You've got something you know that diverges. The one you're working on, all the terms are bigger than those. Doesn't it make sense that you can conclude that diverges also? We've got terms that are all bigger than the terms of a divergent series. If they're all bigger, then, and in this case, positive, right? So everything's positive. You have bigger positive values added together than a series that we know diverges. Conclusion, diverges. All right, so what about, and then the example we did earlier was close to something like, was it 4 over p squared plus 2? Not p, j squared plus 2. And we said that's essentially the same thing as what? P equals 2. And what about that one? We saw that converges to something like 3.443. So why? Because when you have a bigger exponent in the denominator, then those terms are smaller, right? And in this case, enough smaller for then the series to converge rather than diverge. So what's the breaking point? What's the breaking point? Okay, so it turns out, so we're not going to prove it for time's sake, but it turns out that this p equals 1 is the breaking point. When p is greater than 1, the p series converges. But as soon as p gets to 1, and that's the harmonic series, that diverges. And certainly if p is less than 1, that's going to diverge also, because then all your terms are bigger than the harmonic series. So we got to file this in our brain, right? For the sequence, what does p need to be for the sequence to converge? P has to be greater than 0. But then there's so now when we add up the terms, there's like a higher, more stringent requirement on p for those when you add them up for it to converge. And that's p has to be greater than 1. So when p is greater than 1, then when you add them all up, it will level off to a finite value, like we saw in this example here. Okay, so let's talk about geometric series. So we talked about p sequences and p series. We talked about geometric sequences, so what about geometric series? So geometric series is of the form like this. So now notice we have this, so notice there's this coefficient we didn't talk about before. We just said like r to the power of the index, right? So now we're going to also include for the possibility of a coefficient. We'll call that coefficient a. Right, so a number a times r to the, instead of starting at r to the 1, we're going to start at r to the 0. Okay, so see this, think what? Everyone write it down. You see this, and you immediately think what? What does all those scary, not scary symbols mean? Okay, Ray, tell me. But what does this thing equal? So when you see that, you think what? Yeah. So when you see this symbols, what does it mean? So we think what when we see this? What does it equal to? Right, and what is that? What is that? Judith, did you get it? Okay, so God, so this is, we got to have this down. When you see this, you have to know what this means, right? You have to know what this means. If you don't know what this means, you got some catching up to do. So I know, yeah, Stephen. Okay. Right, exactly. It's this. You plug in j equals 1, and you get the first term. Then you plug in j equals 2, and you get the second term. You plug in j equals 3, and you get the third term. And then what does a series mean? It means add them all up. So when I asked you to do this, if you couldn't do this, you have to get caught up. When you see those symbols, you have to think and be able to immediately write that, because we got to know what we're working with here. All right. So the question that comes then is, for what values of R does a geometric series converge? So let's review. For what values of R does a geometric sequence converge? What was that? Not greater than 1. Between -1 and 1, right? Because what is the idea of the sequence? You keep multiplying by one more R. So if you keep taking a fraction of what you had before between -1 and 1, that thing will approach 0. So let's just review that. For geometric sequence, the sequence goes to 0 if R is between -1 and 1. So now the question is, what's the requirement for the series to converge? So now we're going to add them all together. We saw with the P series, we had a higher requirement on P, right, in order for the series to converge. So what about for the geometric series? So don't try to write this down. I'm going to go fast through it if you want to pause it on the video and take notes. So this is just proof of this. So I'm going to consider the sequence, the kth partial sum. Here's the kth partial sum. It goes all the way from A out to AR to the K minus 1. And I'm going to take that kth partial sum and multiply everything by R. And when I do that, I get a lot of common terms there. You see that? I'm going to multiply every term by R. And so then if I were to subtract, all those middle terms would go away. And I would just have A on the here up the left minus AR to the K, because all those middle ones would subtract away. Good so far? I'm going to factor out my kth partial sum. So the kth partial sum is times 1 minus R is this A minus AR to the K. I'm going to divide by the 1 minus R. So it turns out here's a way to express the kth partial sum. The kth partial sum for a geometric series can be expressed as A minus AR to the K over 1 minus R. And that's just by following through the algebra. Okay, and I'm gonna split that apart into two fractions. So we take A over 1 minus R minus AR to the K over 1 minus R. Split that apart. Okay, so the sum of the series, we said, was what? The limit of the sequence of partial sums. And here's the kth partial sum. This is the kth partial sum, and I let K go to infinity. Looking at the limit of the sequence of partial sums. That's this. So the sum of the geometric series is the limit as K goes to infinity of the kth partial sum. We said that earlier in class. Hold on a second. All right, so that's the limit of this. That's the limit as k goes to infinity of the kth partial sum, which we showed by the algebra is that expression. Okay, so this then is the geometric sequence. When does this sequence go to 0? This is a geometric sequence, r to the k. As k goes to infinity, when does that sequence go to 0? When? R is between -1 and 1. So if r is between -1 and 1, this second fraction goes to 0. And we're left with this, a over 1 minus r. So that's what that sum is. So when does the geometric sequence converge? It's the same requirement for the sequence to converge. When r is between -1 and 1. And what does the series converge to? The sum is a over 1 minus r, if r is between -1 and 1. Okay. Did I answer your question? Or?
No, it's actually just a little error in the presentation. Something that might be potentially confusing is on your thing it says AR to the K plus AR to the K. Should it be AR to the K minus 1 plus AR to the K?
Yeah. Okay. Any questions on this? Okay, so let's apply this to, you did the problem for the turtle, right? Let's talk about the turtle. The turtle walked 1/2 the yard the first day, 1/4 on the second, 1/8 on the third. Express it as a series. So as a series, this is 1 over 2 to the j. 1/2 plus 1/4 plus 1/8 plus 1/16, etc. Quick. So this is exactly what the turtle did, right? So now I want to write this as a times r to the j minus 1 to make it look like a geometric series. How can I do that? How can I make 1 over 2 to the j equal to a times r to the j minus 1? So remember, this means multiply 1/2 j times together. This means multiply r together j minus 1 times together. So if we make r 1/2, then how does multiplying 1/2 j minus 1 times compare to multiplying 1/2 j times? How do I make these equal? On both sides of the equation, I need 1/2 multiplied j times together. So what do I need? I need one more 1/2, right? Now I'm multiplying 1/2 together j times, because it's j minus 1 times and one more time. That means a is 1/2 and r is 1/2. And what did we just say? So does this series converge? Yes, because r is between -1 and 1. And what does it converge to? A over 1 minus r. What is a? R is? So I get 1/2 over. And so the sum of the series is 1. 1 whole trip across the lawn. Does the turtle make it?
Assuming that there's infinite.
Right, exactly. The turtle makes it, assuming that it walks for all infinitely many days.
But he can't.
As soon as he stops, that's a partial sum, and he won't make it. But if he does the whole series, right? If he walks for an infinite number of days, the sum is 1. He makes it across the lawn.
That's not logically impossible.
Go back and watch this video. There was lots and lots of stuff.
That's what I said.